Okay, now let's move on to chapter 3, the fuel cell reaction kinetics. In chapter 3, firstly we check difference between electrochemical reaction and chemical reaction. The current generated by the fuel cell, the current depends on the electrochemical reaction, right? So the amount of the electrochemical reaction increased, the current will be increased. Then how can we increase the current and the electrochemical reaction? That means improved fuel cell performance, and by design the catalytic action activity and electrode design, we can increase the electrochemical reaction rate. Action activity. So then what is the difference between the electrochemical reaction and chemical reaction? The electrochemical reaction, the transfer of charge or electron between an electrode and chemical species. Okay, the transfer occur between the electrode and the chemical species. Let's draw of this concept. If there is an electrode in here, that is the electrode, and if there is an electrolyte, in the electrode, the electron can pass through it, and in the electrolyte only the ion proton can move through it. And if there is a proton and the electron, there is a pair of the chemical species including this proton and electron, and in the interface only at the interface they can decompose and they can move through, the electron can move to the electrode, and this ion or proton can move through the electrolyte. And the counter electrode, the electrode and proton can react at the interface by moving through the electrolyte and electrode respectively. So this is the electrochemical reaction. And then what is the chemical reaction? Chemical reaction means as the electrons are not released between the two chemical species, the charges are transferred directly, not through the electrode. The chemical species, in the chemical species, the electron maintain its position, or the composition inside the electrons orbital is changed. So electrons are not released. Then how can we draw this one? The electron, if there is a plus proton and electron pair, and the other a plus electron, and if they meet together in the space and they share the electron together, and the electron is not released throughout the outside of the chemical species. Okay, this is the chemical reaction, and this is the electrochemical reaction. So the released electron we can use the useful work by using this released electron. And now let's take a look at the heterogeneity of electrochemical reaction. The fuel cell, the tri-phase structure or three-phase structure. And there is a gas phase and solid phase and liquid phase. As I said, there is a TPB where these three components meet together. And in the fuel, what is the fuel? Fuel is the gas, right? So the hydrogen gas or the oxygen gas. And in the solid phase that means electrode, right? Electrode, solid means electrode. And in this part, in this phase, the electron can move through it. And in the liquid phase, that means the electrolyte. And in the electrolyte, the proton or ion can move through it. So if they meet together in the only one side, as I said, the interface between electrolyte and electrode, they can generate water molecules. So the hydrogen oxidation, also the hydrogen oxidation reaction also happens in the three-phase structure, TPB. So HOR occurs at the electrode and electrolyte membrane, electrolyte interface. So the hydrogen ions are present in the electrolyte and electrons are present in the electrode. The proton ions are present in the electrolyte and electrons in the electrode. So, and let's check what is the current from now on. The current is rate. Rate means the velocity, right? Rate. So current is the rate value of the electrochemical reaction, right? The rate is very important concept, and the unit is expressed in ampere, and it is also same with the coulomb per sec. So ampere equals to coulomb per sec. So what is the Q then? This is the coulomb. Coulomb means the charge, the amount of the charge. So the current is expressed is like this: I equals dq over dt, and the unit is coulomb per sec. And this charge is generated from the electrochemical reactions. So the rate of the electrochemical reaction, this side, determine the current, right? So how can we relate that? So as we learned, the H2 gas is decomposed into 2 H plus and 2 electrons, right? And if n more of the hydrogen gas is reacted in HOR process, HOR, the hydrogen oxidation reaction, then we can get the 2n H plus and 2n electrode. So that means if we make n more of the H2, then we can generate 2n more of the electron. Right? And what is this one? This is the number of electrons. So we use the small n, right? So if you insert in the Q this value, then we can get the current from it. So also so we can re-express this current as like this one. In here, the capital N denotes the H2 and more of the H2, and this is the more of the electron. So this is the definition of the current. And the electrochemical reactions are heterogeneous, right? To separate these two composition, as this schematic shows, the HOR is the surface limited reaction, okay? Not volumetric. It is surface limited reaction, and it can take place only at the interface, between the electrode and electrolyte. Then let's check the example 3.1 together. The calculation of the amount of the current generated by the fuel cell. So the question is, when 100% fuel is used in STP, 5 ccm standard cubic centimeter per minute hydrogen is sufficiently supplied. What is the current that the fuel cell can generate? In here, let's check the CCM first. CCM, there is a standard cubic centimeter, right? Standard cubic centimeter means there is the volume of the 1 centimeter. So this is the cubic, and this volume means the cc, right? 1 cc, and the m means the per minute. So we can rewrite this one as 5 cubic centimeter per minute. Okay, this is the meaning of this one, and also we can convert it to the liter unit. Then what is the liter? 1 liter equals to the cubic with the one length of the 10 centimeter. So we can use it, and this is the 1 liter. So to convert this one to the liter unit, then 5 cubic centimeter per minute, and we want to get the liter, and 10,000 cubic centimeter. That means 0.005 liter per minute. And we define the L per minute as a LPM. So remember this one. And okay, so this is the concept definition of the CCM. And then let's calculate the current. In this question, we should get the current. Then how can we get this one? Firstly, we define the current as by using the number of electron, that is a 2 in this HOR, and F Faraday constant, and the rate of consumption of the H2 by electrochemical reaction. So by using this one, yes, this one, I equals to NF dN over dt. Then we already know about this N as 2 and F as a Faraday constant. So we want, if we get this one, dN dt, then we can know about the I, current. So to calculate this d and dt, this is the gas state, so we should use the ideal gas equation to calculate it. Then there is a relation between the number of moles and the volume. What is that? PV equals capital N RT. So we want to get the dn dt, the time, and then we can use this equation dt t. But in here, the p and t and r is can be considered as a constant, so this go forward, and rt p t dv dt. Okay, this is the flow rate, right? This is the flow rate in terms of liter per minute. Okay, let's use this one. And if you want to get this one, then you can insert each value in here, p r t, and in the liter unit and atm, we can use the gas constant as 0.082, and this is 1 atm, pressure is 1 atm, and this is the flow rate, and the temperature is the room temperature. So if you insert each value in here, then we can get this one, more per minute in here, right? And if you insert this value into here, then we can get 0.657 ampere. That is the current from the use of the 100% of the fuel, H2, hydrogen gas. Okay, then okay, then let's move on to the next. This is about the current also. Current is an amount. Current is an amount. So how can you get the charge? Charge can be measured, calculated through integration of current over time. So I equals to dq dt. So to get this one, we should integrate this current over time, this one, and the q equals to nfn, right? nfn. So if you want to get that, if you want to the chemical species and the chemical electrochemical reactions of the chemical species, the amount of the chemical species is this n, and we want to calculate the charge from the reaction, then this is the q, right? And if we only the multiplying this nf, then we can transfer the chemical species to the charge. Okay, so remember that nf, and in here the hydrogen fuel cell, this is a 2f, right? Okay, to convert from the chemical to the electrical, then we only it is okay to remember only this 2f. And the current density, let's talk about the current density. In the fuel cell, we usually use the current density, not a current. So the electrochemical reaction is the proportional to the area of the boundary surface. So we want to use the unit area of the fuel cell. So the current density is expressed in terms of J. So J equals to I over A, right? And the unit of this one, remove this one. The unit of the current density, ampere per square centimeter. Then how can we get the electrochemical reaction rate per unit area? What is this? What is the unit of this V? This is the electrochemical reaction rate per unit area. So we can use this unit for it. Mole per sec and square meter. Or square centimeter. Okay, let's use square centimeter. I think it's okay. So if you, this is the rate overall consumption rate of the hydrogen gas, and if you divide the A to them, then we can get the electrochemical reaction rate, right, per unit area. And if you convert this one into the current density, then we can use this one. Okay, in here also in the conversion, then we can use only this one, NF, right? From the chemical species, we want to convert into the dense current term, then we only multiply NF in front of the rate of the electrochemical reaction, right? Of the chemical species. Okay, so remember that NF is the key term in here. NF. Okay, then let's check the potential regulating electron energy. The electron, or what is the direction of the movement of the electron during the reaction? Each reaction, oxidation or reduction. So electrode potential based on equilibrium potential. The negative electricity means the reduction reaction, and positive electricity means the oxidation reaction happens. So electrochemical reaction is expressed as like this one. Like this. This is the oxidant. In the light direction, what is that? Okay, let's choose this. What is this? The oxidant get the electron, right? Electron, and this direction is the reduction. And what is, how can you call the reverse direction reaction? We can call it as a oxidation. Okay, so check the direction of the electron in here. From the reaction, there is an electron generation. Then electron generation, that we can call it oxidation. And if there is remove the electron through the electrochemical reaction, then we can call it the reduction. So let's check the direction of the electron movement in this figure. Okay, firstly, let's see this one. Through this side, the electrode potential increase. So increasing, this is direction for the increasing electrode potential, which means the voltage is increased through this direction. This direction, that means in the reverse direction, the electron energy minus electron energy increasing in the reverse direction. So This is the minus increase through this direction, and this from here and to this direction, the potential, electrode potential, the plus energy is increased through this direction. And each electrode has the electron, the energy state of the electron, right? We can refer to Fermi level to determine that one. And if in the electrolyte there is chemical species, if the electron energy of this electrode, this is the electrode, and there is chemical species in the electrolyte. So the potential of the electrons in each side is fixed. If we fix the chemical species, then this is fixed. And how about that? The electrode potential can be moved, right? Can be changed. And if the Fermi level, the meaning of the Fermi level is the highest occupied energy level at absolute zero temperature. That means 0 Kelvin. Okay, that is the energy state of the electron in the specific electrode. So if in this case the Fermi level of the electron has the higher electron energy than the chemical species in the electrolyte, then the electron can be transferred from the electrode to the chemical species. So we can call it as a negative, right? Negative electrode potential, because it is a higher. It has a higher electron energy. And this reaction, how can you call it? The chemical species obtain the electron, right? Through this reaction, the electron is consumed, right? Then we can call it as a reduction. In this case, the reduction reaction happens. And this is the equilibrium, and there is no, the forward reaction and reverse reaction has the same rate, so it can maintain its state. And how about the third case? In the third case, in the electrolyte, the chemical species have higher electron energy, right? So electron can move through this electrolyte to this electrode, into the electrode. So that means it has the electrode potential has the more plus energy. That means the lower electron energy. So we can call this one as positive electrode potential. So in this reaction, from the chemical species, from the chemical species, there is electron move from the chemical species to the electrode, right? So this is the oxidation reaction. Oxidation reaction. Okay. And furthermore, let's talk about the Fermi level more. And I found some YouTube link for the explanation of the Fermi level. So let's check it together.
In metal, there is one partially filled band which is a result of conduction band overlapping with the valence band. So this is that partially filled band in metals where the conduction band is overlapping with the valence band. So this overlapping results in one big band in which we will be having some field states and some empty states. Now at absolute zero temperature, that is at 0 Kelvin, the lower energy levels in this band will be filled first and upper energy levels will remain empty. We can define Fermi level as the highest occupied energy level at absolute zero temperature. So the highest occupied level at absolute zero temperature, that is 0 degree Kelvin, is called as the Fermi level. So in this case, this is our Fermi level, the highest occupied energy level at 0 degree Kelvin. All the energy levels below this are completely filled at absolute zero temperature, and all the energy levels above this energy level are completely empty at absolute zero temperature. The energy corresponding to this Fermi level is called as Fermi energy, and it is denoted by EF. So at T is equal to 0 degree Kelvin, all the energy levels below Fermi level are completely filled and all the energy levels above Fermi level are completely empty. So we have defined the Fermi energy level as the energy level, highest occupied energy level at absolute zero temperature. But as the temperature increases, you can see what happens. Some electrons from the lower energy levels are going to the higher energy level because they will get some energy with the increase in temperature, and therefore they may get excited to this higher energy levels. So at higher temperature, at temperature T greater than 0 degree Kelvin, the probability of occupancy for all the energy levels below the Fermi energy level may not be 1, and probability of occupancy for the energy levels above the Fermi energy level may not be 0 always. For calculating the probability of occupancy for a given energy level, Fermi and Dirac have written the Fermi-Dirac distribution function, and this Fermi-Dirac distribution function is written as f of E is equal to 1 upon 1 plus e raised to e minus ef upon kt, where this f of E is probability of occupancy for the given energy level E, ef is Fermi energy, k is Boltzmann constant, and T is temperature at which we are calculating the probability of occupancy for the given energy level. This probability of occupancy is very, very important because it can be used to find out the number of electrons actually. If we know the density of states, by multiplying the density of states, that is the number of energy levels per unit volume, if we calculate this if you multiply this by the probability of occupancy, then actually we can calculate the number of electrons per unit volume, that is electron concentration can be calculated. Here this K is Boltzmann constant, its value is 1.38 into 10 raised to minus 23 joules per degree Kelvin. But if you are writing E minus EF in electron volts, then K must be written in electron volts per degree Kelvin, and its value will be then 8.625 into 10 raised to minus 5 electron volts per degree Kelvin, which can be obtained by dividing this value in joules per degree Kelvin by 1.6 into 10 raised to minus 19. If we plot the graph of probability of occupancy of a given energy level E versus energy level E, then the graph will look like this. At 0 degree Kelvin, all the energy levels below the Fermi energy level are completely filled, so probability of occupancy is 1, and for all the energy levels above Fermi energy level are completely empty, so probability of occupancy will be 0 at 0 degree Kelvin. As we increase the temperature for T1 greater than T, that is 0 degree Kelvin, for T1 greater than 0 degree Kelvin, there will be some empty levels created. So as the temperature increases, more and more empty levels are created below the Fermi energy levels, and field levels will be available above the Fermi energy levels. And therefore, the probability of occupancy below Fermi energy level will no longer be 1 always. For just below the Fermi energy level, the probability of occupancy will reduce from 1. And above the Fermi energy level, the probability of occupancy will increase slightly, just above the Fermi energy level. As we increase the temperature further, more empty levels will be available below the Fermi energy level, and more field levels will be available above the Fermi energy level. So probability of occupancy will reduce below the Fermi energy level, and probability of occupancy will increase above the Fermi energy level. So this is how the graph will look like when we plot the graph for probability of occupancy of given energy level versus energy. Graph will
Okay, the Fermi energy level, that is very important in the semiconductor, but also we will not consider again from this time. In this explanation, this graph means this is the Fermi energy level, and this is the probability of the existence of each electrons, right? We can express this one as a probability, right? The quantum mechanics. So in here, in the absolute 0 degree Kelvin, then that means in this graph, okay, the lead one means the electron fill out the electron in the Fermi energy level, that is the highest energy level. And if we increase the temperature, it is like the evaporation of the water surface. Okay, the water can evaporate through this surface, and to some amount of the water molecules is evaporate. So the water molecules can exist in this site, right? And in this blue one, that means the energy, the probability of the electrons is expressed like this one, right? So the electron can reach to this level, and the electron inside this and Fermi energy level, and the probability is lower than this one, right? In the same energy level. And also, if we increase the temperature more, then the electron can go over more electron energy state, something like that. Okay, here's just to think about the evaporation of the water surface. It is similar to this concept. Okay, then okay, let's go
look like
over.
when we plot the graph for probability of occupancy of given energy level versus. So Fermi-Dirac distribution function is written as f of E is equal to 1 upon 1 plus e raised to E minus EF upon KT. So at T is equal to 0 degree Kelvin, for E is less than EF, that means let us consider all the energy levels below the Fermi energy level, and let us try to calculate the probability of occupancy for those levels. So what we are going to do is, now we are trying to calculate the probability of occupancy for all the energy levels below Fermi energy level at T is equal to 0 degree Kelvin. So at T is equal to 0 degree Kelvin, we can write this E raised to E minus EF upon KT to be equal to E raised to some negative number upon 0. Because E is less than EF, E minus EF will result in some negative number, and T is equal to 0. This negative number upon 0 will result in negative infinity. So E raised to minus infinity, that is written as E raised to 1 upon E raised to infinity, that is 1 upon infinity. E raised to infinity will be infinity, and 1 upon infinity will be 0. So at T is equal to 0 degree Kelvin, for E less than EF, this E raised to E minus EF upon KT turns out to be 0. So if we put 0 for E raised to E minus EF by KT, then probability of occupancy can be written as 1 upon 1 plus 0, that is 1. So for all energy levels E less than EF at 0 degree Kelvin, the probability of occupancy is 1. That indicates all the energy levels below Fermi energy level are completely filled at absolute zero temperature. So probability of occupancy for all the energy levels below Fermi energy level at 0 degree Kelvin is 1. Now let us calculate probability of occupancy for all the energy levels above Fermi energy level. That is for E greater than EF at T is equal to 0 degree Kelvin. So at T is equal to 0 degree Kelvin, for E greater than EF, E raised to E minus EF by kT will be equal to E raised to some positive number upon 0. Now E is greater than EF, so E minus EF will result in some positive number. So E raised to positive number upon 0, T is equal to 0, so kT will be 0. So E raised to positive number upon 0 will be E raised to infinity, and that is equal to infinity. So if we put infinity for E raised to E minus EF by kT in this Fermi-Dirac distribution function, the probability of occupancy for the given energy level E can be calculated as 1 upon 1 plus infinity, that is 1 upon infinity, that is 0. And therefore, this indicates all energy levels above Fermi energy level are completely empty at absolute zero temperature. And therefore, probability of occupancy for all the energy levels above Fermi energy level is 0. So, this is also in accordance with the definition. Now, let us try to calculate the probability of occupancy at T is equal to 0 degree Kelvin for E is equal to EF by using this Fermi-Dirac distribution function. So at T is equal to 0 degree Kelvin, E is equal to EF, this E raised to E minus EF upon kT will become E raised to 0 upon 0, E is equal to EF, so E minus EF will be 0. And 0 is upon 0 is something that we don't know, not defined, and therefore we cannot calculate the probability of occupancy at Fermi energy level at 0 degree Kelvin. So probability of occupancy at Fermi energy level will not have a definite value. So there is a transition here occurring in this graph. The probability of occupancy is not giving us a single value. So for E is equal to EF, for E is equal to EF, T is equal to 0, it is not possible to calculate the probability of occupancy by using Fermi-Dirac distribution function. But let us now try to calculate the probability of occupancy for E is equal to EF and T is greater than 0. So for temperature greater than 0 degree Kelvin, for the Fermi energy level, let us try to calculate the probability of occupancy. So now E raised to E minus EF upon kT will be 0 upon kT, E minus EF is 0, T is not equal to 0. So 0 upon kT will be 0, anything divided by 0 divided by anything will be 0. So E raised to 0 will be equal to 1. So E raised to E minus EF upon kT for this condition turns out to be 1. And therefore the probability of occupancy F of E will be equal to 1 upon 1 plus 1. 1 upon 1 plus 1, that is 1 by 2. So whatever be the temperature greater than 0 degree Kelvin, for E is equal to EF, the probability of occupancy will be half. So whatever be the temperature greater than 0 degree Kelvin, at Fermi energy level, the probability of occupancy will always be half. So this is the significance of Fermi energy level now. At 0 degree Kelvin, we cannot determine the probability of occupancy for Fermi energy level. But for the temperature greater than 0 degree Kelvin, the probability...
Okay, that is a very good explanation for the Fermi energy level. And let's check about the limited reaction rate. There is an activation barrier, right? It is also related to the probability. That is the activation barrier, right? To make these two reactants react to generate the product, then they should overcome this activation value. So in here, delta G plus plus is the activation barrier. This impedes the conversion of the reactant to product, right? That is a barrier, right? And because of this barrier, the rate at which reactants are converted into product is limited. So let's check then if there is this graph. Now we see this graph, right? This is the reaction progress, right? From the left to the right is a forward reaction, and from the left to the right, from the right to the left is a reverse reaction. Okay, to make this from the reactant to generate this product, then there should be each step for this reaction. So step by step, let's check the step. And why the charge transfer reaction have an activation energy? Why this reaction have the activation barrier? And hydrogen molecule reaction includes the following basic steps. This is for the only HOR. If the gas transfer, the first step is get H2 hydrogen gas transfer to the near electrode. Okay, if there is a metal, this is electrode, this is the metal atom, and the hydrogen gas should approach near this electrode. And the second step is adsorption of hydrogen molecules on the electrode surface. Right? So the hydrogen molecules bind to interact with the metal electrode. And we call this adsorption, right? So we call this one as a fissorption. And the third step is the hydrogen molecules are separated and chemical adsorption of the two hydrogen atoms on the electrode surface. That means the hydrogen molecules is decomposed and each atoms adsorb on the metal surface. Okay, this is atom, right? So we call this one as a chemisorption. Okay, that is a difference between the fissorption or the chemisorption. And the fourth step is release of hydrogen ions into the electrolyte and transfer of electrons from adsorbed hydrogen atoms to the electrode. That means the adsorbed hydrogen atoms is decomposed as the hydrogen ion and metal electron, right? And the final step, the transfer of hydrogen ion from the electrode to the electrolyte. Okay, so the final step is just that they move far away. This is the fifth step. Moved from the electrode surface to the bulk electrolyte. So there are 5 steps, right? 5 steps, but if there is a very, very slow rate, then that will determine all of these reaction rate, right? So then what is the rate determination step, which is the slowest step? The hydrogen ion electron transfer, right? That is the slowest step. So step number 4, these this step is the slowest reaction. So if we consider about the fourth step, then we can determine the kinetics or the rate of the chemical reaction, right? Then let's talk about this fourth step. The hydrogen atoms, right? The hydrogen atoms firstly can be solved onto the electrode surface, and they are decomposed into electron and hydrogen ions. So this is the schematic of the chemi-solved hydrogen charge transfer. Chemi-solved hydrogen charge transfer reaction. The reactant state, a chemi-solved hydrogen atom, MH, is shown at 1, and completion of the charge transfer reaction as shown at 2 liberates the free electron into the metal and a free proton into the electrolyte. So that can happen. So when we see these two species, this one MH, the hydrogen atom adsorbed to the metal surface and decompose into the proton and electron. So if we see this, the free energy of this, the first one and the second one together, then we can know about the energy state from the 1 to the 2. Okay, then what is this one? One refers to the MH chemi-solved, right? So this in the x-axis, that means indicates the distance from the interface, right? And the second one is decomposition into the hydrogen ion and electron, right? So this is the step for the second energy level, because as the hydrogen ions are far away from the electrode, then the chemical species is satisfied and stabilized when the H plus, this hydrogen ion, goes too far away from this metal surface. So this is the graph for it. And in the first species, if the hydrogen atom is not that stable, right? They should make a covalent bond, right? So from the far away of the metal electrode, the hydrogen has a higher free energy than the instead of the hydrogen gas. So as the hydrogen atom approach to near the metal surface, the state is stabilized in here. And if the hydrogen atoms approach too closely to the metal surface, then because of the repulsion between the atoms, the free energy will be increased. This is from the repulsion, right? So the energy curves can be drawn like this one, right? And then we want to know about, from the first one, we want to know about the step for it. From the first species, the product is the second one, right? So the curves, if we find the minimum energy, easiest way, then we can draw like this. Okay. Okay. We can draw like this. From this start point, the MH is converted through this reaction. So this is the energy level, and this is the reason why there is activation energy for the reaction happen. So Let's check this one. Schematic of energetics of chemical hydrogen charge transfer reaction. The curve one lead. Curve 1 in lead. Curve 1 means this one. As a function of the distance of separation between hydrogen atom and metal surface. And the curve 2 shows the free energy of the product as a function of distance and between the hydrogen ion and metal surface. The dark line denotes the easiest way. Okay, this purple one is the easiest or the minimum energy path for the conversion of this to this. So the activated state is represented by A. So that means this is the activated state. We call this one activated state. Right. So that is the reason why there is activation barrier. Okay. So from this fact, we can anticipate what is the rate determination. Okay. So from now on, let's check the activation energy determines the reaction rate. We should express this one in the form of the equation. So we will use the possibility. So only activated chemical species convert from reactant to the product, right? And activation state probability, that is activation state probability, that is the P, right? Probability of the activated state. So activation barrier size, exponential dependence. Okay, they have the exponential dependence. This is the activation, the amount of the activation energy. So if the activation, okay, if the activation energy barrier is increased, then the probability for the activation state to convert into the activation state will be decreased. And if we reduce this activation energy, then the possibility will be increased. Okay. So, okay, this is the relationship between the activation barrier and possibility, and the reaction rate can be expressed as the multiplication of three components. The reaction rate is the probability is proportional to the probability, right? And the frequency, okay, frequency of decay into product, right? And the third one is the participating reactant. That means that is the concentration, right? This means concentration. Okay, if we see this one, decay, if what is the probability from lead one from this reactant? What is the probability of the conversion into the activated state from the reactant? That is the P, right? Probability. And the second one is from this state, they can react through here, through this direction, and also they can react through this. This is a desirable, right? Desirable reaction or undesirable reaction can happen, right? That is the second one. Frequency of decay into product. Okay, that is denoted by F. This is decay rate, frequency of the decay, and this is the probability. And finally, if there is more participating reactant, that means more higher concentration, then the reaction rate will be increased. So the reaction rate, which is expressed in the form of V1 here, V1 can be defined like this equation. Okay, so this is for the forward, right? Forward reaction. But also, as I said, the reverse reaction can occur, right? From this product, if they go over the delta 2G, the delta G2, then the product also can be converted into the reactant, original reactant, right? That is the reverse reaction, right? So we should, to consider what the net reaction rate, we should consider these two terms, the forward reaction rate and reverse reaction rate, right? So in here, the same one, that is the forward reaction rate, and in here the concentration of the reactant is Cr, and the energy barrier is delta G1. But in the reverse reaction, the concentration is for the product, right? This is for the product concentration, and also the activation barrier is different, right? Because if we see this one, okay, there is a delta G1 is the activation barrier for the forward reaction, and this is the delta G reaction RXN. Okay, from these reaction, the overall the energy is reduced by the amount of them, and the delta G2 is the same with delta G1 plus delta G reaction, right? So that's why in here this is expressed. Wait. Okay. In here the reaction has the minus, delta G has the minus sign, because the final, what I mean is this the absolute value of this one, because this one from this state minus this state, so it has the minus value. So in here we denote this one as a delta G2 plus plus and delta G1 plus plus minus delta G reaction. Okay, we can use like this one. And then the relationship between current density and reaction rate, as we learned before, the J current density and this is the reaction rate, and if we multiply the NF, we can convert from the reaction rate to the current density. Then the forward reaction current density is expressed in this form: NF. Okay, if we just multiply NF in front of it, the reaction rate, then we can convert it to the current density. And the other one is the same with, in here there is a typo in here, C product, right? Product. And also the J2, in J2, if we multiply NF, then we can convert it to the current density. And thermodynamic equilibrium means the forward and reverse reaction current density balance. Then the net current density should be 0. So J1 equals to J0 and J0. Actually, there occur the forward reaction and also the reverse reaction too, right? But the rate of each reaction are the same. So we call this one as a exchange current density. So there is no apparent current density from the reaction, but actually there occur the forward and reverse reaction together. We call this one exchange current density. The J0. So in the case of the forward reaction rate is higher than that of the reverse reaction rate, then the accumulation of metal electrodes and electrolyte. Okay, if the rate of the forward is higher than the reverse, then there should be accumulation of the electron onto the metal electrode, and the electrolyte, there is a accumulation of the hydrogen ion in the electrolyte. So the charge accumulation, this charge accumulation lasts until the potential difference between the reaction interfaces reaches the free energy equilibrium. Okay, the potential. This is the polarization. Because of the polarization between the plus and minus, there occur the potential difference. Okay, in the graph, let's talk about the equilibrium state. In this graph, actually the first one is the chemical free energy, and the second graph is for the electrical energy. So as I said, if the forward reaction rate is higher than the reverse reaction, then there should be accumulation of the metal and the electrons and hydrogen, and they made the electrical potential gradient like this one. Okay, they have the slope between them, and we know about this potential as NF delta pi. Delta pi is the electrical potential. And if we sum up these two potential, the chemical and electrical potential, then we can get this one, right? This one. That means the forward reaction and the reverse reaction has the same activation barrier. That means it is in the equilibrium, right? So at equilibrium, the chemical free energy difference across a reaction interface is balanced by an electrical potential difference. So in the expression in the equation, the J1 is a forward reaction is expressed like this one, and this is the activation barrier, right? Activation barrier. And the second one is the reverse reaction, and they have the activation barrier as like this, right? Okay, then let's compare its value in here. Okay, let's define the delta reaction in here, and the delta G1 original and delta G2 is expressed in this form. And if the absolute value of these two values are the same, then they result in this graph, right? So they go to these two value, sum up of these two value goes to 0, right? Then it is the same with the J1, right? J1 equals to J2 because, and also they are the same. And then as a result, the interface potential for the reaction is higher than the reverse reaction rate. Then the result of these two effects, the delta G1, okay, this is the original forward activation barrier. But if we compare this delta G in the equilibrium state, what is the larger one? When you compare these two, this delta G is higher than this delta G1, right? Because there is a slope in this electrical potential, right? So it is slightly as higher, and by the effect of this potential, this layer, okay, this slope, the free energy of this product increased to here, right? To here, and the graph can be drawn like this, right? This is the result of this one. So that's why this is the delta G. Then delta G, this is delta G. So if we compare this to the delta G1, this is higher than the original one. And how about the delta G2? Then delta G2 in here, this is original one, and only this is the delta G, the after making it as a equilibrium state. Then the delta G gets smaller. Delta G gets smaller to reach this delta G plus plus. Okay, and if we see into the anode and cathode too, because from the electrolyte that the proton and electron polarized, so, and also there should be electrical potential difference between two, and there is for the amount for the anode and also for the cathode too, right? So one hypothetical possibility for the shape of the fuel cell voltage profile is expressed in this figure, and since the scientists can determine only E0, right? We can know about the E0, but not for each delta pi for anode and delta pi for the cathode. So we cannot determine this one, and we only can determine E0 in here. The galvanic potentials at the anode and cathode of fuel cell must sum to give the overall thermodynamic cell voltage. Okay, that is the concept of the equilibrium. Okay, and this is the equilibrium first, and let's talk about the potential and late Butler-Burma equation. The current density equation for forward and reverse reaction. We can determine the J1 as a forward reaction, J0, and this term. This is the exchange current density, right? They have the same one. And what is this one? Okay, let's talk about this. Firstly, okay, that electrical potential makes it as a equilibrium, the blue line, right? And there is a original delta G activation barrier in here. And how about the case if we decrease the amount of this value, the electrical potential, we can sacrifice, that means the sacrifice of the electrical energy with the amount of this value, okay, then the energy curve can be drawn as follows. Okay, then what is the meaning of this curve? Okay, then there is a change activation barrier in the forward direction, and there is the reverse direction activation barrier also changed, right, from the original. Then that makes the accelerate the forward direction than the reverse direction, right? That means the forward direction is dominant than the reverse direction, and we can make a current and from a chemical reaction, apparent chemical reaction, and also we can extract the current from this chemical reaction. That is the meaning of this one. So that is if we sacrifice this value of the voltage in terms of the voltage electrical potential, then we can break the equilibrium state, and we accelerate the forward direction than the reverse direction. So if the galvanic potential across a reaction interface is reduced, the free energy of the forward reaction will be favored. Okay, favored is proper word. Forward reaction is favored over the reverse reaction, while the chemical energy of the reaction system is the same as before. Changing the electrical potential upsets the balance. That breaks the balance between the forward and reverse reaction activation barrier. So in this diagram, reducing galvanic potential by F eta reduces the forward activation barrier, right? When we compare this blue one and this red one, the activation barrier gets lowered, right? This gets lower than the previous in the equilibrium state, and increases the reverse activation barrier. Okay, the purple one. Okay, purple one. This is the delta G2, right? Delta G2 gets higher than this one, right? Than this one. Okay, that's it. And we can express the current density as like this one. But let's check this one. This amount of the electrical potential is reduced, or reduced for the delta G2. Okay, this one. So how can you express this one? If there is a delta G plus, okay, and then the plus minus alpha NF eta, and then okay, minus for this one and plus this one. Minus this value and plus minus NF eta, and in front of it there is a minus sign. This is the and we can conclude that this is included into the exchange current density, right? This is for the exchange current density, and when we consider this one, plus minus alpha minus 1 and f eta, right? This goes for this because there is minus. Okay, okay, let me see. Okay, they goes to this term exponential minus 1 okay, minus 1 minus alpha nf eta. So it goes to this term. Okay, so that is the current density for the reverse reaction. And how about this one? From this blue, from this blue, the activation barrier change to this red one. Okay, then from this state, the change of the activation barrier is just alpha nf eta. So in the forward direction, this one, alpha nf eta is expressed in here. Okay, so then the net current can be expressed from the J1 minus J2. So this is the exchange current density, because this is the same one. They bind together, and that is for the forward, and that is for the reverse. So this is the meaning of this is equation for the Butler-Bulmer equation. Okay. So remember that this is for the forward direction, and this is for the reverse direction, and this is the exchange current density. So if okay, let me see, if there is a higher exchange current density, if we see the reaction rate in the equilibrium state, there is no apparent reaction, right, in the equilibrium. But actually, if we have the higher J0, then if we sacrifice a small amount of eta, that is a eta activation over potential, then we can generate the high current density, right? So that is the exchange current density, means the potential for the extracting of the current. That is the meaning of this one. And also in the Butler-Bulmer equation, additionally to this equation, we also consider about the concentration of each product and reactant in here. So this is a final or general form of the Butler-Bulmer equation, which express about the kinetics and reaction rate for the chemical reaction. Okay, that's it for today. And before end of this class, let's see this one. This graph. Extracting a net current from a fuel cell requires sacrificing a portion, that is very important, sacrificing a portion of both the anode and cathode galvanic potential to the amount of this one. So we call this one eta activation. Okay, activation over potential. We should sacrifice to generate the current. So in this figure, the anode galvanic potential is lowered by this amount, while the cathode galvanic potential is lowered by this amount. So as the figure indicates, eta act A, eta act C are not necessarily equal. They are not equal. And actually, at the cathode potential is generally much larger than this one. So it is higher than this one. And this is the operating voltage, what we get. Okay, that's it for today. We learned about the fuel cell reaction kinetics today, and also we learned about the Butler-Bulmer equation and the sacrificing of electrical potential to generate current.